Mark. Hello. Quarter da. How's everyone? Good.
Yeah, good.
Have you been to B-Sides before, or is this your first time?
No, first time for us.
Good. Well, hopefully you'll enjoy it. So this talk's a little bit different. Usually when I come to these things, I talk about security stuff. Security is what I do for a job. I lead an AppSec team for a company called Matillion. But I also like doing other things. And one of the things I like about the security scene, the hacker scene, is that actually there's a lot of people that are into all sorts of different stuff, right? And I wanted to share some enthusiasm. And where I wanted to start with this is that I remember my first computer. Do you remember your first computer? My first computer was brilliant, right? It was absolutely fantastic. It had 32K of RAM. It could display 8 colours, right? I could read programs from the tape, or get this, discs, yeah? And it could do sound, and I could share programs with my friends at school. Sometimes we'd get them printed out and type them in. And it was brilliant, right? And computers are even better now, right? I've got a computer in my pocket that's apparently more powerful than the computer they used for the moon landings. My car has got computers. It's got computers on the computers. It's got computers on the brakes. The charger for my car has got computers in it. The display adapter for my other laptop has got a computer in it. They're everywhere, right? But they're also a little bit disappointing, aren't they? You know, if you told 6-year-old me that I'd have a computer in my car and I couldn't play Chucky Egg on it, I'd be really, really sad. Okay. And so what this talk's about is it's mostly about how to recapture the fun of having computers that do exciting things for you. So that's what I'm hoping to do. And so the talk is about building robots. But what is robot? Does anyone want to venture an idea as to what a robot is? Any ideas?
A fun companion.
A fun companion. Okay, that's not a definition I've heard before, but I like it. Okay, last time I gave a talk like this, someone said it's someone with no personality. Yeah, that's pretty good, isn't it? Okay, so I'm going to talk a little bit about what I am going to talk about, which is I'm going to talk about things like this. Okay, so my journey with this subject started when one of my kids came to me, and we used to have a summer holiday project, and one year we made a go-kart, and the next year my younger son said to me, "Daddy, yes, can we build a robot to mow the lawn?" And I'm like, first I'm like, no, that's ridiculous. We can't build a robot to mow the lawn. And they're actually like, you know what, that's a really cool idea. And the thing is though, you can't just go to like a shop and buy parts for lawn mowing robots. So first we had to build a 3D printer to make the parts, and then we built this robot, and this is the first version. And this is just a machine that's controlled by computers, right? And it's a little bit like what people think about when they think about robots, because it moves around and it had a camera and a little display and stuff. But it could also be something like this. Can anyone tell what that is from looking at it? Anything in the picture you recognise? It looks like a potato. It's actually eggs. It's an incubator. Well done. Right. So this is a robot I built, which is a Linux-powered chicken mama. It's a box with a heater in it and a little Raspberry Pi and a humidity sensor and a temperature sensor. And when it gets too dry, it blows water through this bit here to make the air more humid. And when it gets too cold, it turns on the light under that foil and it warms it up a bit. And then a few weeks later, those eggs turned into chickens. It was magic, right? But that's kind of like a robot, isn't it? It's a computer that does stuff. Or, continuing on a theme here, can you see a theme? Well, so when the chickens appeared, we wanted ways of keeping track of them. So we had computers that kept their environment warm, gave them food, took pictures of them for us. I was very bored during the pandemic. Chickens were my friends. Continuing theme here, this was a computer-controlled door to open and close. Can anyone guess what it's for? It's for chickens, right? It's a door that opens and closes and lets the chickens in and out, and it serves an important purpose, right? It stops the fox from getting the chickens, right? But all of these things are kind of robots. They're computers that can sense their environment and do things, and so that's what we're talking about. We're talking about physical computing. And actually, you know, if we're going to be really strict about it, well, most of the computers we use can sense and affect their environment, can't they? Because, you know, I'm looking at a screen now, and when I touch it, it does stuff. But I'm talking about how to build our own, you know, how we can make our own things that sense or affect their environment. So let's make a start. Who does a bit of programming? Anyone done some programming before here? Okay, can anyone tell me what this program does?
Not compiled because there's no semicolon at the end.
It's Python. Come on. Someone knows the answer.
It outputs hello world.
It does. It outputs hello world, right? And this is like the definitive simple program, isn't it? You run it, and it has one piece of data that deals with the string hello world, and it puts it out on the screen. So what we're going to do now is we're going to do hello world, but with physical computing, right? Now, a word of warning. Everything you see here is live, which probably means something's going to go wrong. It might mean everything that goes wrong is going to. It might go wrong is going to go wrong, and that's okay, right? You know, this is like tech talks is an adrenaline sport. I'm okay with that. So what we're going to do is we're going to find a program that I made earlier, Blue Peter style, and we're going to make it do something. So I need an output device. What can I use as an output device? I've got an LED in this bag. You know how hard it is to type when people are watching you? This has a close cousin on like motor skills generally. So I've got to put some leads on an LED and plug it into something. It'll be fine, I'm sure. Okay. So you saw me start up the camera program earlier on. The reason for that was I wanted you to be able to see what I'm doing. Okay, so you can see here, what I've got is an Arduino. Other single board computers are available, other microcontroller development boards and stuff. And what I'm going to do is I'm going to put one of the legs of the LED into one of the I/O ports on the Arduino and the other one on the ground, like this. And if you go to the diagram on the slide, oops, there we go. I've got a little circuit diagram. That's what's going on here. And then we're going to find a program and run it, and then that LED should flash. Okay, so let's find our program. File open. Okay, so really simple program. We're telling it that we've got an LED on pin 11. Actually, I don't want that one. I want blink. Let's get a different one. Common says blink, right? Well, it will blink, but I want it to blink differently. We want this one instead. There we go. So we want no input here. So literally just an LED. We tell it that the LED pin is an output pin, and we have a loop which will turn the LED on and then turn the LED off. It'll sleep for a second after it's turned it on. It'll sleep for a second after it's turned it off again, and it'll do that over and over again. So let's plug this in, and then we'll pray to the demo gods. Whether you want it to succeed or fail determines which prayer you give to the demo gods. And then hopefully when we run this, we'll be able to see a flashing LED. Okay, and file, actually just, there we go, upload. So what this does, it builds the Arduino project, it sends the code to the microcontroller, and with any luck, so microcontroller is here, camera is there, LED is there, yay! Success! Okay. Diolch. Who speaks Welsh here, by the way? Anyone speak Welsh? A little bit. I've been learning because my nan was Welsh, but I'm not very good. It's hard, like properly hard. Okay, so that was Hello World as a Arduino project. Okay, so let's go back to some slides. Okay, another program. Can you guess what I'm going to ask here? What does this program do?
not sanitise the input.
It doesn't. You're right. It takes some input and then it uses that input to generate something to output. Okay, so it's a little bit like the last one, only it's taking some input. So how are we going to do some input? Any guesses? A button. Yeah, that's right. So got a button in here. Okay, so this is a micro switch. Okay, it's called a micro switch because it's a switch and it's small. Okay, closer look for those of you at the back. Looks like this. It's got 3 little legs and a little button that you can push down. And when you push the button down, it closes the contact between this leg here and this leg here. All right. And what we're going to do is we're going to find a different program. This time, the one that I opened before when I meant to open the first one, and it's expecting an LED on pin 11 and a button on pin 8. Okay. So let's go to our circuit diagram so I can explain what's going to happen when this works. Okay, so pin 11 we have the LED, like we had before, and on pin 8 we have a switch. When the switch closes, the input voltage here changes. Now there's a little detail here which I'm going to tell you about and then you can completely forget about for the rest of the talk. If you've got an input on a microcontroller board or something like this, you can't be certain that it has a particular voltage to start with, right? It just sort of floats around. And so when you put a switch on it and close the switch, it might do something, or the computer might not realise anything's happened. Okay, so what that means is that you need to make sure that the voltage is something to start with, and then it changes when you press the button. Okay. Now, you can mostly forget about this because most of the boards that you'll use have little built-in things called pull-up or pull-down resistors. And it means that to start with, your pin 8 will be, in this case, pulled up to 5 volts, and when you close the switch, it goes back down again. So just imagine a little resistor between the 5 volt line and here, because that's what's going on inside the Arduino. You can normally forget about this as long as you realise that that's a thing, and if something is going weird, that might be something to check. Okay, so the important part here is we've got our LED on pin 11. We're going to take our switch and we're going to put it between pin 8 and the ground. Okay. We've already had one demo work. Those bad at statistics will tell you that makes this one less likely to. Okay, so we're setting up an LED on pin 11, a button on pin 8. We are starting the delay to 1024 milliseconds. We're setting the LED pin to be an output. We're telling the button pin to be an input that's pulled up to 5 volts. And we've got a loop that turns the LED on, waits for a delay, turns the LED off, and then if the button's being pressed, it halves the delay time. Okay? So it'll start flashing on and off roughly every second. When I press the button, that time is going to reduce. Or at least that's the theory. I have no idea if it's going to work. Let's find out. So it's flashing, that's a good start. Okay, yeah, I just wanted to make sure it worked before I put it on camera and cheated. Okay, so let's reset the board. So we've got the light blinking on and off. You can see that okay? I'm going to press the button now. And it's blinking faster. And if I keep on pressing the button down, it blinks so fast that you can't even see it's blinking anymore, right? Now, what do you notice about that, the brightness of that, compared to the brightness of that? Anyone notice anything? It's roughly half, okay, and that's going to become important in a moment, all right, when we talk about another concept in a moment. Okay, so there we go. That is our equivalent of Hello Mark, right? So far, so good. Okay, so I mentioned that the fact that the LED sort of dimmed when it went really, really fast was important. The reason for that is that when you've got a digital system like a microcontroller, you're dealing with on and off, right? What happens if you want your sort of shades of grey? Well, the way it works is you're actually dealing with different amounts of on and off when you're thinking about outputs, right? And this is something we call pulse width modulation, because when something's sort of on, or sort of half on, as an analog output, what's actually happening is it's turning it on and off very, very quickly, And how much it's on versus how much it's off determines how much on the thing is, right? So LEDs, you can change the brightness two ways. You can reduce the voltage, but that doesn't always have the desired effect. Firstly, the output of the light compared to the voltage isn't linear. Secondly, the colour changes, right? Similarly, if you've got a motor, if you turn down the voltage, it's more likely to stall and you're more likely to burn the motor out. Whereas if you turn them on and off again really, really quickly, they behave themselves and you get the effect that you want. Okay, so that little demo where it was halving the sleep time every time until it got down to a millisecond is useful because it shows you like a 50% pulse width modulation. So that would be a teeny bit on, that would be a teeny bit off, and that would be sort of somewhere in between. Yeah, have I explained that remotely coherently? Brilliant, fantastic. Okay, now we've done that, we can move on to analog stuff. Okay, so here we have another diagram. Does anybody know what the symbol here means? It's a variable resistor, yeah. So it's a potentiometer. One side of it is on ground, the other side's on our input voltage, and there's a bit that can move on the in-between. And this is connected to one of the analog input pins on the microcontroller, yeah? And when you turn the dial on the variable resistor, because the one that I've got here has a little knob, I'll show you the camera, there we go. So when I turn this, the resistance between the red and the black leads here, you see, and the yellow one changes. The yellow one is at one end effectively close to the black and at the other end effectively close to the red. Okay, so what we're going to do now is we're going to attach this leg here to the ground on the microcontroller board, this one here to 5 volts, this one here to the analog input pin, and then hopefully we can run another sketch that will allow us to have an analog input into our microcontroller. Have I explained that okay before I move on to actually failing to put the board together probably? There we go. So black in the ground, red in, I've dropped the LED, that's not what I wanted to happen. There we go, and that's in the 5 volts. I'll put the LED back on and then we will update the sketch that it's running. I'll be honest with you, I'm already surprised how much has worked. It's got no right to go this well. I've doomed the rest of it, of course.
Yeah, I was about to say, you did know.
Right, so we've got an analog program here, and this is more or less the same as the one where we were reading the button value. It's different in a couple of minor ways. So let's upload the program to the controller, and okay, I've actually made a mistake here, but it doesn't matter because it'll still work. Right, so I've got an output pin again, the LED's on pin 11, I set it up as an output, and then I probably should have set up the analog pin, but it kind of doesn't matter because the Arduino will mostly do it for you. But in the loop, all that's happening here is reading a sensor value. Okay. Now, the Arduino Uno, which this board is here, has a 10-bit analog input, and when you're doing analog output, it has an 8-bit output. So what we're doing is we're taking the input, we're dividing it by 4 because that makes the maths work, and it means that the amount that the LED is on is proportional to the amount that the voltage is on the input pin. Does that make sense? Sort of. So hopefully that's going to work. Again, a little prayer to the demo gods, please. Oh, and the LED's fallen off. What I can do, in fact, that's probably a good idea. What I can do is just put the LED in the board. If it falls out again, I'll do that.
How come this time you didn't use the pin mode output pull-up?
Well, so we needed the pull-up for the input, not the output. So because there's not an input that isn't analog, we didn't need to pull up. There's kind of already threshold set for the analog because the one end of the potentiometer is on ground, the other end's on 5 volt. And so when you turn it, it's somewhere between the two. So it's always going to be something that you expect. And here you see I'm turning that potentiometer, and the LED is getting brighter as I turn that up and down. Okay. Now, what we're going to do now is we're going to leave the hardware completely the same, aside from me dropping things and having to put it together again. Because what I want to demonstrate here is that once you've built some hardware, because this is a system that you've built, you can change what the hardware does based on the software that's on it, right? So, same hardware, we're going to change the program, and this time we're going to bring in a different component to the system. And the name of this project is Analog I/O plus Serial. Can anybody guess what I'm going to do?
Right back to the console.
Yeah, we're going to interact with the console. Okay, and actually, this is a really useful point, because one of the first questions I get when I show people this sort of thing, one of the first questions I get is, what should I use? Because there's a dazzling array of stuff that you can buy for doing these kinds of things these days. So you've seen the Arduino I've got there. You might come across these things here. So this is a Raspberry Pi 2040 microcontroller board here. So it's on a little project board. You can see that tiny little thing there. But let's take it off so you can see how big it is. Don't want to break it. There we go. So that's another type of board you can use. This is another microcontroller. Or you can even get little single board full featured computers. So this here is a Raspberry Pi computer, which rather than being a microcontroller is actually a fully featured computer running Linux. You can actually do stuff on. We have one there doing something with the AV. But you can build projects using either of these. And so people very often ask the question, which should I use? And the short answer is that for most applications, or for some applications, it doesn't really matter. It's mostly about the tools that you use and what you're comfortable with. If you like writing software, for example, in JavaScript and Node, that's your preferred ecosystem, you're obviously going to be happier on a computer that can run those things than something that can only do C, for example. And the Arduino uses C and C++. But there are some important differences. So, for example, microcontroller boards typically have richer, low-level I/O options. So we've used an analog input pin there. There's no such thing on a Raspberry Pi. Yeah. And they're often simpler to get running because all they run is the single program that you put on it. You know, the program that you've burnt into the ROM on the controller when you press play on your Arduino IDE or similar. It's only got that to worry about. Single board computers can do more. You know, they're running Linux, so you can put whatever services you want on here, including your favourites of machine learning libraries or whatever. And they can run a full OS with all the benefits that'll give you, like, you know, network connectivity and all that sort of stuff. But they come with drawbacks. You know, one being fewer options for I/O, another being that actually you've not got quite as much control over the real-time aspects of the I/O. You know, if you need something to happen within a few milliseconds, well, actually, I'm sorry, you've got to wait for the Linux kernel to schedule that, right? And so I sometimes use one, I sometimes use the other. Very often I'll use both. And this is where we're going to sort of go with the analog and serial example in a moment. And that is that if you've got different devices in your arsenal, you can make use of the benefits of them in the ways that you want to without having to be constrained. So the first robot we saw, we had that little green 3D printed thing. It had an Arduino in the base, yeah, doing all of the I/O to motors and sensing where the motor encoders were. And it had a phone on a stick, which provided virtual telepresence robot stuff, virtual telepresence software. So it had a version of Firefox that I'd hacked to allow it to talk to Bluetooth on the Arduino, and it used WebRTC to allow me to control it from the remote browser. Right? So you can make use of both of them. You can't run Firefox on a microcontroller, and neither would you want to, but you can run it on a phone. You can't run your favourite dev tools on a microcontroller, but you can probably run them on a Raspberry Pi. So being able to use both can be really, really useful. And with that in mind, let's go back to the example. So what we've got here, we've got this analog I/O program, uses exactly the same hardware, but it's making use of the cable between the computer and the Arduino to give us access to a serial console. So we're going to run this program now. And then what we're going to do is we're going to get a tool called a serial monitor. And it's gone onto the second monitor because of course it has. Okay. And we're going to tell it to show us. Of course it's not working. Does it show? There we go. It's showing us what the value it's reading from the analog input is. Okay? So if I turn that potentiometer and tell it to show me again, there we go. It's going up. And it should go all the way up to 1023. There we go. And then what we can do is we can make it change the behaviour at runtime. Okay, so we've got our camera here. I'm going to move this over to one side. At the moment, if I go from all the way clockwise to all the way anti-clockwise, it takes me from being all the way on to all the way off. And if I tell the program to reverse the input, now when I go all the way clockwise and go all the way anti-clockwise, it makes the brightness go up. So it's reversed the effect of the input, right? And so this starts to give you the idea that you can take these systems, which in their basic form are actually really, really simple, and by using software you can make them do different things. It's essentially a configurable thing that you've just made, yeah? So, for example, your incubator might just use a Raspberry Pi because it needs to be able to run a program. It needs to be able to do digital I/O, but it doesn't need to do anything fancy. But being able to talk to it from the house is really useful. Yeah, your phone on a stick robot. You use the phone for the brains. You use the microcontroller to control the hardware. Working together is really, really useful. Okay, have I explained all that? Okay, brilliant, fantastic. So. Actually, before we talk about this, have you seen this before?
Yeah.
Right, so apologies for the next bit because we're going to go a little bit, draw the rest of the out. But before we do, I just want to introduce a thing, okay? So we've used a couple of different types of, well, we've talked about a couple of different types of analog output. We've used an LED, goes from sort of completely off to completely on, and you've got bits in between. You can do that with motors as well, right? Okay. But sometimes with motors, you don't just want them sort of off to fully on and something in between. Sometimes you want them to go the other way as well, right? And how do you reverse the direction of a motor? Anyone know? H-bridge. Brilliant. Okay, so that there is an H-bridge driver. It's a thing that allows you to not only turn the motor on and off and in between, it also allows you to swap over the power so it goes the other way, essentially, in simple terms. Okay. And what it does, it gives you two motor outputs. You've got motor A, motor B. It gives you 4 input pins. And the way I've configured this one, you give it input on this pin, and it'll make the motor go in one way. Input on that pin, it'll make that motor go the other way. And then the other 2 pins, same for the other motor. Conveniently, this board, it's an H298 board that you can get on eBay for about £1.50, I think. Will also allow you to take a 12-volt input, and it'll give you a sort of vaguely stabilised 5-volt output, which allows you to power your microcontroller or little computer. Okay, and so what we're going to do is we're going to take that and use that to make a slightly more complicated version of what we've already seen. Okay, so there are 4 digital outputs here. 9, 6, 5, and 3. Those go to those 4 pins that control the motor one way or the other on each side. And then we've got another thing here. Can anyone guess what this is? Sorry? It is a Wi-Fi or Bluetooth card. Specifically, it's a Bluetooth card, and it's one of these. Again, you can get them for a couple of pounds on eBay. And what it does is it gives you a device that you can plug into a serial port, and then you can connect to it from a Bluetooth device, like a phone, and then you can send data, similar to what we were doing over the serial monitor there, but over Bluetooth, right? So we can take what we've already learned from the serial example, apply it to 4 pins instead of 1 LED, and instead of physically connecting a USB cable to the computer, we can connect this instead and talk to the microcontroller over Bluetooth. So it's exactly what we've seen, it's just more of it, right? Now this is the bit where it's all going to go horribly wrong, because I've got to put that together now while we're here. Okay, so what's your level of confidence? Yeah. You've got faith in me, this is lovely.
Good track record so far.
Oh yes, well, so far so good. What I'm going to do before we do anything else though is I'm going to put the correct program on the microcontroller, because we're going to unplug it from the computer, and hopefully once the power comes from the battery pack I've got, everything's going to work okay. So just to show that I'm not cheating, here we have an Arduino project called Bot Software. Those 4 output pins, LF, LR, RF, RR, left front, left rear, right front, right rear, for those 4 motor pins. Those 4 motor pins there, yeah. And then I set up the serial for the Bluetooth connection, tell the output pins that they're output pins, and I loop over, and I'm listening to the Bluetooth input for some strings, and I decode the line, and then I tell it to move the motors. Okay, and if you want to read more details like that, feel free to come and find me afterwards. I'm not going to read C code now, because that's even less interesting than me talking. Okay, so that's what we're going to try and do now. Did I press go on that project? I don't think I did. Let's do that. Okay, so it's done that. Wish me luck. Okay. Now, so what I did here, obviously with the example I showed you before, this is something that me and my kid built, right? It was a phone on a stick thing. Who 3D prints their own robot parts here? Fantastic, brilliant. The 2 of us in this room to do that, right? So it's not very accessible as a way of doing stuff. So I thought, how can I make this a little bit more accessible? So the next thing I did was I went on Amazon looking for robot chassis or toy chassis, and I found this, right? So this is I think it cost me £4. It's a little plastic thing with 2 motors, and it had a little battery pack and just fly leads coming with the motors. And I thought, well, that could be interesting, but the motors were rubbish. So I took some motors out and put some better ones on, chopped out the battery pack because it wasn't powerful enough, and then realised that actually, you know what, we're in building your own stuff territory again, and that's not really what I wanted. But the point is, we've got all the parts here that we were talking about. We've got our H-bridge driver here. Underneath, we've got a couple of motors here. And so when we plug all this in, we've got exactly what we saw on that diagram a moment ago. So I'm going to unplug this from the laptop. I'm going to start plugging this in. So the first thing I need, my Bluetooth adapter thing here needs some power. So let's connect that up first. I need the red one to go onto 3.5 volts, and the ground to go onto ground. So hopefully Bluetooth has power. Now I need the Bluetooth serial lines, and what I've done here, I took a photo of how it's supposed to look so I can put it together without thinking, because thinking is a thing that's, again, harder when there's a room with people watching you. And these are supposed to go on pin 10 and 11 here, because that's how I've set up software serial in the Arduino project. Okay, now what I need to do is I need to power the Arduino. So I've got 2 power leads here. The red one goes on 5 volts. The, not black, but it's the closest to black I could find, goes on ground. Okay, so the Arduino should have power now. Now what I need to do is I need to connect up those 4 motor control leads, and those go on. You're going to go and tell everyone that the most dull talk in the world, he was telling me what colours he was plugging in. Red, Where's it gone? Oh, there it is. Now, that's the wrong one. That's why. Look there. Red, brown, yellow, and blue. So red goes in 3. Brown goes in 5. So these pin numbers, these are PWM output pins on the Arduino. They're not just sort of random numbers that I've chosen for fun. Yellow goes in 6. And blue goes in 9. And then because I've done the wrong ones for power earlier, I need to fix that. 9. And then once we've done this, and this again is, I apologise, a slight draw the rest of the L moment. I wrote a program for my phone that talks to this over Bluetooth. I'm happy to share that program with anyone that wants to play with this sort of thing in their own time. Again, I didn't think you'd want me to live code that while you were all watching. There we go. So now, this is all connected up except the 5 volt lead keeps on falling out. It's going to do that again. I know it is, but I'm at peace with that. And now I just need to add another battery because that's how I turn this on. And there are blinking lights. Blinking lights are a good sign, right? Okay. Lights are blinking. I'm going to tuck a couple of leads in so that it doesn't pull itself apart as soon as we try and make it move, because that's a very real risk here. It's also entertaining, so I'm not going to try too hard. And then I'm going to put it on the floor. There we go. So I wrote a program on my phone. What it does, it gives you a little UI that tells you that you can connect to the Bluetooth thing if you want to. And then if you touch in the middle of the screen, it does nothing. If you move your finger up in the middle, it drives the motors forward. Oh, something's wrong there. If you... Oh, I've wired 2 of the things the wrong way around. It still kind of works though, look. But there you go, I'm controlling this with my phone. And that was a tiny little program on the microcontroller, and a couple of little bits of hardware, and woohoo, we've made a little radio-controlled toy. Isn't that cool? So there we go. There we go. So, like, total cost of that, including the microcontroller, is like less than 20 quid. If you use the newer, cheaper microcontrollers like that little Raspberry Pi board, you're probably looking at less than a tenner, actually. Okay, so the very, very final bit, that's still not very accessible because you've got to buy a thing and cut it up. So I thought, how can I make this even more accessible? See what I'm doing here. So, Lego make a series of toys called Power Functions. And so what I did was I bought one of those kits and I figured out how the wiring works. Got these little plugs. These 2 here are always ground and 5 volts, and the other 2 switch over depending on what the Power Functions kit's supposed to be doing. And then electronically, it is identical to what we've just built. So it's got the same H-bridge driver, it's got the same microcontroller, it's got the same Bluetooth thing. And so if I turn this on, get my phone out. Yes, I'd like to connect. Please. Oh, there we go. There we go. So, now that is how to build robots for complete beginners. Thank you very much.
Any questions? Yeah. What age did you start teaching your son to try and build stuff? I mean, when do you think was too early or about right?
They still enjoy it even when they don't understand what's going on. so like my daughter is just turned 8, and she enjoys playing with them. My son was probably 11, 12 before he sort of really understood what was going on. And you know, he can write bits of Python and stuff now. So he's been playing with things like MicroPython on the Raspberry Pi 2040. Yeah, they get different things out of it at different ages.
What is a project that you're most proud of?
Probably the chicken coop one, actually.
Yeah, that's fair.
The reason for that is it's actually useful. I made it because I had an unfortunate incident where I forgot to shut the chickens in one day and the fox got them. And so knowing that that once they go in, the door closes is a really good thing. I've got little RF chicken like bird rings on their feet, so I know when they're all in.
That's so cool.
And so when it gets dark, if the door closes and they're not all in, I know to go out and check on them and stuff. And, yeah.
That's really smart.
So that's probably what I'm most pleased with. Yes?
Probably a bit of a weird one. Do your chickens have names?
Do the chickens have names, and if so, what are they? Yes, they do. So we have Buzz, that used to have a friend called Woody that sadly is no longer with us. We have Elena, because my daughter's favourite TV programme for a while was Elena of Avalor. We have Beryl, which was taken in by a neighbour who found a chicken wandering at random down the road. No idea where that came from. And we have one that's called Purple because the ring is purple. And there's another one, and I can't remember which one I missed out. Yeah. So we have. But we used to have 12 at one point, including a cockerel called Kevin, who was a bit scary. Thank you very much.
Thank you.